All right, recording is rolling. It is Tuesday, November 28th. Yesterday, we started a new topic, rotational dynamics. And a lot of that focuses on torque. I'll give you guys a torque review because later today, we're going to do a torque lab. You guys have a lab paper on your desk. So, in time, we're working towards that. Okay, so we're going to do a quick review. Then I have some demos lined up for you guys. All right. Okay. Right, so yesterday, one of the things you guys saw was this right here. This is one of the big ideas from this unit, torque. All right, really doing R cross F. My two classic examples are a wrench turning a nut, which you guys can see right there. And my other classic example is opening a door. This could be like the door hinge, and here could be the door handle. You're doing R cross F, right? So some radial distance crossed with the force. The cross means you only multiply the perpendicular components. That's all I care about. So this magnitude, and the sine of the angle between them. So it's really this times this. That's what it comes out to be, right? Right. That's also equal to I times alpha, which is important. You should know that today it's not going to come up so much, right? So this is a good picture to have in your mind for the topic, right? Now, one of the ideas I was telling you guys about, how's right-hand rule coming to those, right? Is that if you wanted to find the direction of torque, because these are all vectors, right? Radial distance can be a vector, force could be a vector, because there's directions involved with both those, right? Torque is also a vector. And the way that AP wants you to define directions for torque is either counterclockwise or clockwise, right? But one of the things I was talking about yesterday was that, well, you need to stand in a certain position in the room to be able to determine that. If you stand on this side of the paper, this looks like counterclockwise. But if you're on the other opposite side, you would say clockwise. So which way is it? But everybody can agree on the convention if you come up with a universal convention, and that's what right-hand rule is. Now, AP will not ask you about right-hand rule, expect you to know this, but this is a more universal way to determine this mathematically. And there's more things you can do with cross products with matrices. And I do want to show you guys an example of that today. So in a few minutes, I'm going to flip my screen over and show you guys an example of a cross product solved with matrices, right? And some stuff you can do with that. All right, so hold on to the idea. It's coming up later. Okay, that's next week kind of stuff. Or equilibrium. So you guys know the forces have to sum to zero. You've known that for a few months now. Right? And then yesterday, we tagged on the last condition for true equilibrium, which is that the torque also sums to zero. Now, on a two-dimensional plane, it's just these conditions right here in this gold box, right? Which is pretty much the scope of this class. That's kind of all APL stuff. Yeah, we're on a 2D plane like this. This could be like a 2D plane, XY plane, something like that, right? Clockwise, counterclockwise, right? Right. If someday you're an engineer designing some big 3D building, maybe you have to think in 3 dimensions, and then all 6 of these conditions open up. So there's a little bit to know there. Right? Then, here I've got these two equilibrium examples. I got the seesaw here, right? You guys see like a seesaw? And here's this other example. It's like a scaffolding, right? There's a couple of ropes here, and you can like walk back and forth here. Right? So this is like a 2 halves of a giant torque lab. Right? Today we're going to do this lab. This will be like the last 20 minutes of class. We'll do the seesaw version of this lab, right? And then tomorrow we'll do the scaffolding version, right? And then in the back of my room, in the middle of the room, have one of these worked up. Okay? Right. So there you go. There's a quick review. All right, and that's sample for later. Okay. Right. So there you go. There's a torque review. So R cross F. Hold in. Right. Next thing then. The spool. Ooh, look this right here. Right, so you guys see, do you guys see 2 different size circles? I got like an outside diameter and an inside diameter. Right, this small circle on the inside. Right. Oh, and I've got a string wrapped around the inside diameter. Look at that. You guys see a string wrapped around? Right. Right. So here's what I do with this. We're gonna pull this a few different ways. Right. Now, if I pull this so that what if I pull the string like here, let's start real easy, right? What if I pull this to the right? What if I pull this to the right like this, right? And the question is going to be, which way does this roll? Does this roll clockwise off to the right or counterclockwise off to the left? I think everybody's going to get this. How many here, show of hands. How many guys say it's going to roll clockwise off to the right? Clockwise off to the right. You guys think so? All right. Let's do some actual empirical science. Let's check. Oh, yeah, it's clockwise to the right. Probably no surprise to no one. Right? How about this? What if I pull straight up, like straight up, right there? Straight. How many guys think it's still clockwise to the right? Still clockwise to the right? You guys think? Okay, let's check this out. Is it clockwise to the right? Pull straight up? Yep, still clockwise to the right. Okay, so no surprise so far. Right? Now, what if I put this whole thing upside down, right? And then, so the string's wrapped around the other way. Right. How about if I pull straight up here? Do you guys think this way is going to go counterclockwise to the left? You guys think? Maybe it's just the mirror version of what we started with, so that should be true, right? Yeah. Okay. So symmetry, counterclockwise to the left. Right now here, you guys ready for the tricky question? That all right. But only maybe half you guys get this and half you miss it. I don't know. It's just making a guess. But we're gonna find out. What if I pull in this direction? So here's the tension force, right? Right. This is the tricky question that a lot of students get stumped on, right? If I pull this way, does this still go counterclockwise to the left, or does it roll off clockwise to the right? I'm pulling to the right, right? Let me see, show hands. How many guys think this is actually going to roll counterclockwise to the left? How many guys think it's going to roll clockwise to the right? Ooh, that is like a 50-50 split, right? So let's find out. Let's find out. Moment of truth right here. Right, so I've got the string on the bottom. Right? Then I pull to the right, and it does go to the right. It goes clockwise to the right. Look at that. Right? Now, this has something to do with torque, right? So something to do with R cross F, right? If you were thinking like relative to the center of the circle, right, like radial arm crossed with the force, that would have led you to the opposite answer, which would have been the wrong answer, right? Because this wheel is not actually rotating about its center. The pivot point is actually down here, right, where there's a friction force with the floor, right? In fact, if it weren't for this friction force, this wouldn't actually rotate at all, right? It would just move without rotation. If this was like hovering like an air hockey puck or something, right? It wouldn't actually rotate because there would actually be no torque. There could be a force, but there would be no torque, right? So the fact that there's a force here. So there's as I'm pulling to the right, let's just play off that last example, right? There is a friction force that's resisting, that's pulling back to the left. Now, there might be a net force so that the pulling force is more than the friction force. So overall, it's accelerating to the right. But here is your actual radial arm. So I'll label that R. There's your R, and there's your F. There's R cross F. And if you didn't see it before, now do you guys see this is going to be actually a clockwise torque? That's why it went off to the right. Remember yesterday, one of the things I mentioned with the rotating wheel, but let's say there's a car, and this is one of the wheels on the car. Okay, the car's going 60 miles an hour. The center of the wheel, pointing radar gun at that point, goes 60 miles an hour with the car. Okay. But what did I tell you guys yesterday? Or you guys told me maybe. The top point of the wheel is actually traveling how fast compared to the road? 120 miles an hour. Yeah, like twice as fast as the car, right? Now that's only for that instant. And then what about this bottom pivot point? It's traveling how fast? 0 miles an hour compared to the road. Again, that's just for one instant. So it's actually pivoting about this point right here. Hey, if I pulled upward and this thing rotated left counterclockwise, and then I just shifted the string down parallel to the ground and pull up, went up to the right clockwise, do you guys think that there's some place where it transitions in the middle, where it transitions, and you would get no torque? There's no torque. That would be no rotation. Can I pull this where it slides across the paper with no rotation? Can I have it? Right. If you look at this sticky note here, maybe you'll see that it actually doesn't rotate if I get the angle right. So we get the angle right here. Right about there. You see it's sliding without rotation, right? So there's a net force, right? So then moving it with, right? But there's no rotation, there's no torque. Look at that, right? And what would that line up with this diagram? Well, let's see. If the angle I have to pull it at would be the angle so that I can backtrack, right? And I could extrapolate backwards. Oops. I could extrapolate backwards, and it would head straight towards this pivot point. Kind of like if you push right on the door handles of the door, there's no torque, so it never actually rotates the door, right? You guys see that? I got. There's a guy on YouTube. You might know his channel. You guys know a guy named Steve Mold YouTube channel? Okay, yes, some of you guys do. Some don't. All right, there's like a million YouTube channels out there. I'll write his name down. Steve Mold. Right, he does a bunch of physics engineering stuff. I know he had a version of this spool where he did all the stuff that I did, and he went some extra steps, and he went like all crazy with this, and it's got like a whole video. I think if I remember right, he actually even had a version where he like pulled one direction and actually didn't rotate the other way. He had some crazy rig. So if you want to check that out, that's out there too. All right. Cross product stuff. Okay, so now let's get to that right hand rule stuff. Now remember, in this class or for AP, we're just going to keep torque on like a 2D plane, like an XY plane. We'll just talk in terms of like clockwise and counterclockwise. That's all AP is ever going to ask you, right? All right. But if you want a bigger picture of this, let me give you guys a real complicated 3D example and give you guys some extension ideas here. Right? Here I've got two vectors. I've got them set up. R equals this and F equals this. Now these are vectors. These are going to be in 3 dimensions. Let me draw a 3D coordinate system to draw a picture of exactly what I'm talking about. So I need an X, Y, and Z axis is what I need. Oh, I meant to make that more dash looking. Right. So these are all axes. Here's my X axis. Here's my Y axis. You see like an XY plane, right? And here's the Z axis right here, right? And right at the origin, I'm going to have a nut, right? Here's a nut, right? It's all rusted over, right? So I need to attach a wrench to it to apply a torque to try to like break the rust. So I need to turn that nut, right? It's right at the origin point, right? Right. And here, this tells me how the wrench is oriented and how I'm applying a force. So the wrench is now the I, J, and K. This doesn't refer to imaginary values. This refers to axis directions. I think this is kind of like a coordinate, like 3, 5, -7, right? Except it refers to a vector. Have you guys ever seen vectors written this way? Right? Maybe, right? So 3i, 5j, -7k. That's like x, y, and z direction. So if I go 3 in the x direction, point, point, point. 5 in the y direction, point, 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 point. And then -7 in the z direction, 2, 3, 4, 5, 6, 7. Right? Think of this here. Go 3, 5, down 7. Right? That would be like the end of the wrench is right here. So here's the end of the wrench. Right. And then this wrench is hooked up to this nut right here. So I'm trying to ultimately turn this nut. Right. Right. And right at the end of the wrench is the point that I'm going to apply a force. What's the direction of force? I could apply a force in any crazy direction. Right? Now, if it happens to be parallel to the wrench, of course, it's going to result in 0 torque. But any other direction, there's going to be some kind of torque that opens up. Right. And if it's pushed perpendicular somehow to this crazy like, wrench in this 3D space, then I get like maximum torque for that force. Right? But here's my force. So that 2, -6, 4. So it's like, see, 2, -6, 2, 3, 4, 5, 6, and then +4, 3, 4. So 2, -6, 4, right? That's like, now you have to think in 3 dimensions. That's kind of, if I start from the origin, it's kind of headed off that way. Okay, is what that would be. Now I'm going to connect that back with at the point of the handle of the wrench. So my force is like pushing kind of this way. Right? You have to think in 3 dimensions. It's kind of hard to represent on a 2D paper, but you guys get the idea, right? Okay. So if I'm doing R cross F, here's my R, label that R, right? And here's my F for the direction of the application of force, right? So there's gonna be some kind of torque that opens up, some kind of turning moment in like this 3D space, is that right? And actually that torque will be about some like 2D plane, right? Okay. So how can I like mathematically determine exactly what that torque is going to be? Well, that'd be the cross product of these two vectors. You can only take cross products of two vectors, right? They both have to have an associated direction, right? So, and the resulting vector from that is going to represent also a vector, right? It has a direction associated with that, right? Now, I chose this crazy example because I happened to find a YouTube video that, oh, look at it, it's the same numbers as on the example. Look at it, same numbers. You guys said, right? Except instead of R and F, here he's calling it A and B. You guys said A and B, but I'm calling it R and F because I'm doing a torque example for physics, right? Where did I find this? So I'm on a YouTube channel called The Organic Chemistry Tutor. Found an example of a cross product, right? He's going to solve this with a matrix. I think yesterday, some of you guys said you had seen this and some of you guys hadn't, right? So we're going to do a quick crash course, right? So here's a cross multiplication of two vectors. This is how you figure out cross product, right? I'm going to beat this guy and narrate this myself, right? So this is just a process you have to memorize. Either you take a math class where a math teacher shows you, or you independently on your own time figure out how to do this. You set up what's called a determinant. I'm going to do I, J, and K to represent the X, Y, and Z directions. You just copy paste these values: 3, 5, -7, point, 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 2, -6, 4, point, 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 right? And we're going to take what's called the determinant of that. How do you do that? Well, zoom ahead a little bit. So you write down the I for the X direction. It has nothing to do with the imaginary. It's just X direction, right? And then the determinant of these four. So that's 5, -6, -7, 4, point, 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 point there. That's another determinant. You always do minus J. J is the Y direction, right? It's 3, 2, -7, 4, point, 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 right? And then plus K to represent the Z direction. 3, 2, 5, -6, point, 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 point. We're going to take some determinants. How do you take the determinant of a 2 by 2 matrix? You do, in this case, like 5 times 4 minus -7 times -6, right? You get a number, and then here, I'm going to zoom ahead a little bit, right? Oh, so he's here. It's kind of skipped past. He just told you how to do that, right? Hey, what are we? Hey, the sports person. Got my screen. And then out of this, we're going to get right, a vector that he's calling C, right? See where he has C with the arrow above it to represent a vector, right? Now I would call that torque. I would write the Greek letter tau for torque because that's what R cross F would be, torque, right? He's calling C, right? ABC. And oh, look at that. Negative 22 in the X direction, negative 26 in the Y direction, negative 28 in the Z direction, right? Now that's as a single vector, but you guys remember that's like perpendicular to some kind of clockwise, counterclockwise motion of a torque on a plane that's perpendicular to that, right? So there you go. That's exactly how you find that, right? Now we're only a third of the way through this video, so what else we got, right? The next thing he does, I'll show you guys too. Now, can you guys imagine in your head that that torque is necessarily perpendicular to both the radial and the force, right? The radius and the force. It has to be. The torque is, right? Do you guys remember a few weeks ago when we did work equals force dot distance? Right now, force dot distance came out to units of joules. Right, R cross F has similar looking units. We've got meters and got newtons, but I'm always going to describe torque in Newton meters, never joules, even though it looks like you want to, but it's a completely different concept, right? All right, but here, back to dot product. Dot product, you always multiply parallel components. So if you have, let's see if you guys follow this, guys. If you have two perpendicular vectors and you only multiply the parallel components, isn't there nothing to multiply? Because there's nothing in common parallel, which would always be zero. So the next thing he's going to do is he's going to do math checks. So, well, let me make sure they didn't make some silly arithmetic mistake. If I do either R dot torque or F dot torque, it has to zero out. So zoom ahead, right? Right. So he goes and explains that, right? And he just checks his math. So now he's doing a dot product. Look, it's A dot B. Well, okay, I don't know what he's doing. A dot B. Let's do, I care more about A dot C, or you could do B dot C, right? It has to zero out if he did the math right. And it comes out to zero. So it's like, okay, so I probably did make a mistake while I, okay, you guys see that? Right. Now that's what we just did was we multiplied together two three-dimensional vectors. We got radius in some 3D space, we got force in some 3D space, and we got torque in some 3D space, right? What matrices can also be good for is you can multiply, you can come up with you can do like 20 dimensions if you want to, right? So for example, let's say someday you study economics and you're crazy economist going on, right? And you want to solve some problem. We got like 20 different variables going on. We got the labor force participation rate, we got the inflation rate, we got the poverty rate, and we got the, we got like all these like 20 different variables going on. We say, what if I introduce minimum wage? How is that going to, right? You can set up like some crazy like 20 by 20 matrix and you can like solve stuff, right? All right. So just for this class, everything I just showed you is a bit beyond the scope of this class, right? But you see, it's there, it's out in the world. You can do some crazy fun stuff mathematically with that. And yeah, you might see that in college, maybe. Yeah, good chance your college instructor might pull that. Right. All right. Any questions about that? All right. Next thing, I want to show you guys results from that energy and momentum quiz that you guys did. Most of you guys took this the day before Thanksgiving break. All right. So here's the results. AP, I have 2 different AP classes. That's this graph. I have 4 different honors classes. That's this graph. All right. So how'd you guys do? The average score for AP was a 79 standard deviation. I think like about plus or minus 30-something%, 14.5, right? And then honor students, the average grade was 69 with standard deviation of about 18.7. There you go. That's the results of that. I also have for you guys some Paul Hewitt demos. All right, so let's watch some Paul Hewitt. Most of these are on torque, and then I have one on conservation of angular momentum. There you go. Paul Hewitt. Where's the center mass of a donut? No? All right, so he doesn't actually answer it in this video. So let's see if you guys get this. All right, and remember he solved it right at the point of center of gravity. That's where he could balance it on his finger. All right, all right. So which weighs more, the brush or the handle? Let's see. Show of hands. How many guys say the brush weighs more? Brush weighs more. Close says the brush weighs more. Brush weighs more. Yeah, brush. Yeah, right. Because that's a huge weight. Here, imagine from the point of view of his finger as it was balanced before he solved it. Right. Imagine that's like the pivot point. Right. You guys are going to do a very similar lab here in a really soon, in a few minutes. Right. If you have a huge weight times a small radial distance from that pivot point, that's some torque. And then this handle, the center of mass of the handle itself is probably about here-ish. Right. Now it doesn't have as much weight, not as much force, but it's a huge radial distance. Right. Yeah, so the brush has to weigh more. The brush weighs more than the handle. That is pretty neat. Oh yeah. All right, so let's switch over to your lab. All right, you guys got a lab paper in front of you. I'm gonna walk you guys through an example of what we're doing with this. Right. So this paper has two sides. We're gonna save the other side for tomorrow. Right? So make sure you're on the side that looks like a seesaw. And by that I mean okay, I see a meter stick, I see a couple of weights hanging down, and I see you're holding this up with a spring scale, and you have all those materials on your desk. Okay, so, so I'm using one spring scale to hold this up. Right, probably kind of a all right, just balance. Right. On the back side of this paper is the other setup, like the scaffolding, where like there's two spring scales and like one weight. We're gonna save that one for tomorrow, right? So we're all on the side with looks like a seesaw type setup, right? You guys got that? Like seesaw, right? Right. So, and see, you look at these two pictures; they look identical because they're supposed to be. Now, everybody in class can have a unique setup with their teammates, right? But the idea is like whatever one setup you have, you can use the exact same setup in your table with the other one, right? And there's two different perspectives, and we're trying to figure out what is some unknown weight, what is the mystery weight, right? I think I may told you a story the other day. Like I've done this a few times throughout class. Like if I want to know the weight of like some object, right? Then I could just set some object, set a meter stick, take an object of known mass, put it on one side, and unknown mass the other side. And it's like pretty much identical to what you guys are doing today, right? You can use torque equilibrium to figure out the unknown mass. Right? You guys see on the title it says mystery lab weight. You guys see that? Right. So kind of the goal of this lab is to figure out what is some mystery lab weight. Now you're going to know what it is as soon as you attach it because there are numbers stamped into the lab weights, right? But let's make believe that you didn't know. You're going to do this whole process with torque. You're going to calculate ideally what should have been, and then say like, oh, hey, does that like match what I know it to be? Right? Like for example, guys, 200 grams. How many newtons does this weigh? Like 2 newtons, right? Maybe a shade less than two, but we'll call it two, right? Well, if you do all the calculation, it comes up like 1.95 newtons. We go, oh, that's pretty much 2 newtons. Okay, so you're good to go, right? Right. So how are we gonna do this? We're gonna do this from two different perspectives, right? One that I think is a bit more intuitive, one that's maybe a bit more mathematical abstraction, although the math ends up being straight to a little bit easier, right? Let's start with the one that I think is a bit more intuitive, which is the one on the right. You guys see this detail right here in bold that says pivot point scale? You guys see where it says pivot point scale? Right? You guys see that? Right. So this is pretty much matching this poster is what this is, right? Like I said, I got a seesaw. There's there's this like fulcrum here, and I'm treating this as the pivot point that I'm going to sum the torque about, right? So the pivot point, if I mark it, it'd be boink, that point right there. You guys see that? Right? And I got a couple of lab weights hanging, right? Do you guys think the heavier lab weight is going to be closer to that pivot point, and the lighter one's going to be shifted further away? Kind of like my picture. I guess that, right? So I'm summing the torque about that point. Now, let's say you're allowed to know what the left mass and the left weight is, right? But let's make believe that you can't figure out what the right one is. So you just shift around until you reach equilibrium, where it all balances out. And we're going to use the fact that torque had to sum to zero to calculate what weight would have led to that outcome, to the equilibrium in the first place, right? So let's do moments here, right? So treating this as the pivot point, this weight on the left side, well, it's at some radial distance to the left, so I'll call that R. It's got some weight, maybe I'll call it F for force, R cross F. Hey, is that causing is that a counterclockwise torque? I'll call it tau sub L, the left torque. Okay, set? Okay. Dude, please put the spring scale at the 50 centimeter mark. I don't know if I marked that very well here, but put it at 50 centimeters, probably to do that anyway. Okay. So that it aligns with the center mass of the meter stick, in which case the upward force from the spring scale and the weight of the meter stick itself don't cause any torque about the center, right? It's like if you push right on the hinges of a door, it never turns the door, right? Okay, but what about this mystery weight on the right, right? Well, it's got some different radial distance to the right. Maybe that's like R to the right or R2, right? It's got some different force, probably not as much weight as my picture is shown, like shift away out, right? And hey, I bet this is causing a clockwise torque. I'll call it torque on the right side, right? Clockwise torque. Do you guys think that this counterclockwise torque and this clockwise torque exactly balance out? They better, right? And you're going to use that like in principle to solve for this weight, right? Let me give you guys some example numbers. I'm about to write down some numbers. Don't copy what I'm going to write. I want you guys to do this yourselves, do your own setup. But let's say I had this whole rig in front of me right here. Right? So I'm going to say the left weight is how about this guy? And this guy is 5 newtons. So I'll say he's 5 newtons. Right? And what's this? Left position minus the scale position. Let's say this is like at the 30 centimeter mark, and this is at the 50. Guess what is 30 minus 50? 20. Right? And also be negative. I gave you the negative sign. If it's supposed to be negative, I went ahead and typed that in for you, so can't like lose track of that. Right? Oh, torque is R cross F. What is 5 times negative 20? Negative 100, and the unit is Newton centimeter, right? Negative 100 Newton centimeter. So there's how much torque. Saying let's go counterclockwise. Is that right? Now the weight of the meter stick is approximately 1 Newton. Let's just go ahead and use 1 Newton for the meter stick itself, right? But we're going to make believe all its masses in its weight is at its own center mass, which is perfectly fine mathematically. But we're also treating that as the pivot point for this perspective, which means the torque zeroes out. So I just went ahead and zeroed that out for you. Right? The spring scale has to hold everything up. I'm just going to make up a number, but it doesn't matter what that number is because it's also at the defined pivot point, so the torque zeroes out anyway. You guys see that? Right. So, guys, what is anything plus 0 plus 0? It's just itself. I'm going to copy paste that number right here. So I'm just doing torque accounting. So this number has to be that number according to this perspective. You guys see that? Has to be equal. You guys see that? Right. Right. So in theory, if the torque zeroes out, there must be some restoring torque so that the sum total of torque is 0 Newton centimeters. What does that restoring torque have to be? How about positive 100 Newton centimeters, right? So I'm going to take this number, just invert it, make it a positive 100. So this number, just make it negative, so negative, right? Okay. Right. And then I say, well, where was this mystery weight position? Let's say I don't know what the weight of this is, right? And so, well, okay, I got it at the far end. That's at the 100 centimeter mark. Guys, what is 100 minus 50? Is that 50? And that's exactly what it says to do right here. So 100 minus 50, so like 50 centimeters, right? Your last step, you're going to take, I listed down here a torque formula. You guys see torque equals R cross F? Can you take your torque, divide by R, and that tells you F? Because what is 100 divided by 50? 2 newtons. You guys see that? 2 newtons, right? Right. All right. The left side of this lab is, you don't have to change the setup. Don't even touch the setup. You're just holding it the whole time, right? All we're going to do is we're going to shift perspective. Now, we're still trying to figure out lab mystery weight. I wonder if we're going to get the same number. I hope I still get 2 newtons for the weight, right? But you guys see pivot point 0 centimeter mark? You guys see that? Right? I'm defining the pivot point as that point right there, which might look like an arbitrary point because it is an arbitrary point. This is kind of mathematically abstract, right? I'm pretending, I'm making believe this is the pivot point, okay? Right? Now, mathematically, it's actually a bit more straightforward because the exact positions of each of these forces, you just like write down. You have to take any differences of positions, right? Right? So here, I'll sketch this up. From the point of view of the 0 centimeter mark, this weight is causing a clockwise torque. The entire meter stick has a little bit of weight, so it's causing also a little bit of clockwise torque. This mystery weight is causing a good deal of clockwise torque, right? And the spring scale, well, now you definitely have to get a good reading from that spring scale because that is providing the counterclockwise torque that's holding everything back in check. And now you have 4 torques, and they all have to sum to what? 0 Newton centimeters, right? So if you add up these 3, keep track of, you got 2 clockwise and 1 counterclockwise to opposite directions, right? You're going to get some number. And then this one has to balance everything, it has to restore it to 0. And then you can, in principle, also calculate what weight that is. Okay, you guys get the premise? Right? So you guys got the rest of the class to do this. Try it both perspectives with that one rig. I'll walk around, help you guys out, and we'll save the scaffolding half for tomorrow.